All right, we're going to be studying something for the next couple days that it it's quite confusing, and it's kind of a lot of work to figure it out. Although looking through the problem set, they've kept it much simpler than it could be. It's called partial fraction decomposition. Now, the first time I learned partial fraction decomposition, it was in one of my calculus classes. I don't remember if it was here or not. And my teacher taught me how to do it, and anyway, we set it up, and I just didn't understand why you would want to do this. Now, not, not why are we doing mathematics, but we set up this system, followed the rules, and we set up all of these partial fractions, and I had no idea why that was useful. And then later in my higher calculus classes, we started using it to solve problems, and I understood the purpose behind it. So I'm going to give you the purpose first, so you're not lost for a whole year like I was. So let's say I have some fraction plus some fraction equals 7/12. Okay? Can you tell me what the original two fractions are? No. We don't know what the original fractions were. Okay? But provided simplifying didn't happen, so let's say that 7/12 was the answer without simplifying. Now, there are an infinite number of fractions equal to 7/12, right? So if we ended up simplifying, then there are an infinite number of possibilities. So let's say that the actual denominator is 12. We didn't simplify it. What can you tell me about these two fractions? So first off, the original fractions could have been divided by 12. They both could have been 12s. What else? Not 24. If they were 24s, then I added them together and I simplified. So simplifying never happened. One could have been a 6, and the other one would have been not a 2. How do I know it's not 2? Yeah, if I had a denominator of 6 and a denominator of 2, then my end denominator would be 6. So the common denominator of 6 and 2 is 6. So if one of them is 6, the other could be 12, or, Tyler, I heard you say it. Oh, so that's another option. So I could have a 3 and a 4, or I could have a 6 and a 12, or I could have a 6 and a 4. But wait a minute. 6 times 4 is 24, and I said we didn't simplify. But, right, 6 times 2 is 12, and 4 times 3 is 12. So I know that the least common multiple of my two original denominators was 12. So they both might have been 12, or one could have been a 3 and one could have been a 4. One could be a 2 and the other could be 2 times 3 is 6. So if one's a 2, the other one would have to be 12. The least common multiple of 2 and 12 is 12. If one of them was a 1, then the other one would have had to have been a 12. Okay? Now, these groups are called partial fractions. So all of the partial fractions in this case are all of the factors of 12. So they could have been anything along this range. Hopefully this makes sense. The original denominators could have been 1s, or 2's, or 3's, or 4's, or 6's, or 12's, right? Now, I have no idea what they were, but those are the only options if that simplifying didn't happen. Okay? Now, if I told you what they were, and I also gave you one of the numerators, could you figure out the other numerator? Yeah. So we're going to be doing the same things with rational equations, where the bottoms are variables and quadratics and worse. And we're going to be giving you a common denominator that will be a couple quadratics multiplied together, and then we're going to say, what are the possible partial fractions? What did the original fractions look like? And because we will give you the numerator, you can actually work backwards and figure out what the original partial fractions were, what the equation was before you added it together. So basically, we're going to do this. So I said, okay, this fraction plus this fraction equals 17 over 20. Okay? If I know that, what are the possible partial fractions? Well, it could be something over 1, and something over 2, and something over 4, and something over 5, something over 10, and something over 20. Those are all of the partial fractions. Now, if I told you which fractions I actually used, you know, if I said we used the 2, and we used the 5, and, well, let's just say the 4 and the 5. We used the 4 and the 5. Could you tell me what the original two fractions were? So if I use this one and that one, it's really easy to figure out what those numbers were. Okay, that's what we're going to be doing, only I'm not going to tell you which ones we used. You're going to have to figure it out. Okay? So let's start with something pretty easy, and hopefully we can establish the rules before we dive into the work. So if I had a bunch of fractions added together, I don't even know how many there are. But when I'm done, I end up with this. Over, let's say, a squared b to the third. Okay, so when I add the fractions together and simplify, because we will be able to simplify it in this version, we end up with 15 over a squared b to the third. What could my original fractions have been? What could the denominators have been? Well, it could have been a squared b to the third, right? So a squared b to the third could have been one of them. Okay, so this is the original fraction, and the whole point is to break it down into partial fractions. So that is not a partial fraction, it's the actual fraction. It's the full fraction. So we're going to treat the a's and b's different. We could have had an a squared, but we also might have had just an a, right? We might have just had an a. Okay, we could have had just a b, or a b squared, or a b to the third. Well, we're gonna treat those separately. We're gonna treat each factor separately, because you could do it that way, but in the end, it's gonna end up canceling, and you don't need to worry about it. So what you do is you look at the factors of the denominator, and you look at any sub fractions of that. So how do I get a squared b to the third? Well, it's made up of a squareds and a's and b's and b squareds and b to the thirds. And you might end up not even needing that, but we're never going to do thirds, so we don't even need to talk about that. Okay? So what if I had this? we're gonna start by listing them. Okay. Okay. So here I can factor this. So we have x squared, x minus 1, x plus 1, x squared plus 1. And luckily, none of the ones today are going to be bigger than quadratics, which is going to make your life a lot easier. Okay, so what are the possible partial fractions? One of the fractions may have had an x squared in it, or just an x. Okay, what else? I could have had an x minus 1, or an x plus 1, or why didn't we factor x squared plus 1? It didn't factor. X squared plus 1 is prime. In fact, it has two imaginary roots. Even if the roots were irrational, we still wouldn't, if it's not factorable, we don't factor it, or we don't worry about it. Okay, so I want to point out, this x squared is just a double copy of this x, right? This x squared is part of a factor that has x squared in it. Okay, and that's going to, I'm not going to get rid of that. I'm going to do another one, which is x plus 1 squared, x squared plus 2x plus, better not do that. Sorry. X squared minus 2x plus 1, and x squared plus x plus 1. What are the possible partial fractions for this? X plus 1, that could have been one of the original denominators. But I also need to put x plus 1 squared. So if you look up here, x is a single copy of the factor x. But there are two of them, so x squared. So if I did it the same way here, I would put a squared there, and then x plus 1. Does that make sense? So x plus 1 could have happened by itself or as a squared factor, just like x could have happened as x or x squared. Okay? Then what? Well, does this factor? Yes, it factors to be x minus 1 and x minus 1, which is really just x minus 1 squared. So what are two other partial fractions? So x minus 1, well, to keep it in order, let's square that, and then x minus 1. Okay, what about the last one? That one does not factor, so that is a possible partial fraction. Okay, now here's where it gets tough. Well, here's where it starts getting tough. Okay? What are the numerators? What are the possible numerators? Okay, we're going to do something that's not going to make any sense today. But if you learn the method, then tomorrow you'll see why it's important. So what we need to do is go through and introduce variables for all of these positions. And we always just start with capital A, and we do A, B, C, all the way down. But the size of the numerator is determined by the degree of the denominator. So you guys know what proper and improper fractions are, right? So 4/5, proper or improper? What did it do to be, or no, let's do this one. 7/6, that's improper. What did it do to be improper? The top is bigger than the bottom. So when we're dealing with rational expressions, improper rational expressions have a larger degree on top than they do on bottom. Okay? And then proper rational expressions have a smaller degree on top than they do on bottom. And if the degrees are the same, they're neither proper or improper. Okay? Now, having said that, we look at the degree of a particular factor. And again, this is kind of confusing because some of the factors are squared and some of them aren't. So the factor here, both here and here, is x. That is the factor. The degree of the factor is 1, x to the first. Now, this looks like a quadratic, but in terms of partial fractions, it's the square of a linear factor. Okay? So this one is a linear factor, right? This one is a linear factor. This one is a quadratic factor. It's not the square of a linear factor. Does that make sense? You have to understand that difference, or there's no way you're going to be able to work this out. No, that doesn't matter. The position of the squared is not important, but that's why I did the second one. Is this factor linear or quadratic? The factor is x plus 1, right? Because there it is. That factor is linear. Okay? This is just a square of the linear factor. Okay? That one, is that factor linear or quadratic? It's linear. The factor is x minus 1. We just happen to have a duplicate copy of x minus 1, which is why we had to square it. So this one is a linear factor, and that one is a quadratic factor. So this is the same as that. It's the square of a linear factor. Okay? And this is even though it's x squared, it's a quadratic factor. This one is a quadratic factor. Right? We break it down as far as we can. We cannot go lower than a quadratic on those two that I just circled. Does that make sense? Okay, so for every factor, you have to create a polynomial that's as big as possible and still make the rational fraction proper. Okay, now luckily we're only going up to quadratic, so it's going to be really easy. Okay, and again, I told you this is going to be really confusing at first until we start solving it tomorrow or the next day, and it'll get better. So I'm going to put a up here. Okay, it's a times x to the 0. I'll write that up once, and I'll never do it again. X to the 0. Now, this is a proper, let's write, okay, b x to the 0. X to the 0 divided by x to the first is still proper. Right? Now, this factor is the x factor. The x squared is just a square of the linear factor. So even though this is x squared, it's not considered a quadratic. This is considered a quadratic because I can't break it down any further. Okay? So I'm just going to go through A, B, C, and keep going until I run out of letters. And again, this is going to look really weird. Just hang on. So this will be without those. I don't need to put those. A, B, C, D. Now I get to the quadratic, and I'm on letter E. So it's going to be EX plus. So EX plus F. I know, hang on. So what I've done, I have a quadratic in the bottom. So my numerator needs to be linear. Quadratic in the bottom, numerator needs to be linear because I need it to remain proper, and the degree of the top has to be 1 less than the degree of the bottom. Okay? So, now here's a question. What if you ordered it one way and I ordered it the other way? Our A, B's, and C's are going to be all mixed up. Doesn't matter. However you write it, it's going to work out. Now, if you write it one way and I write it one way and we solve part of it and then we share information, that's going to mess everything up. But it doesn't matter what order you write these in, it will work itself out in the end. Okay? So down here, I would do A, B, C, D, and then EX plus F. Okay? All right, so let's say my partial fractions were x plus 1, x plus 1 squared, x, x squared minus 3, x plus 1, x to the third minus 4, x plus 1. Okay, all of those are factored as far as they can. Okay, this is a linear factor. It's just an extension of that. Does everybody understand that? So these two get treated the same. They're counted as linear factors, but because my common denominator had a linear factor squared, then it could have ended up being once, or it could have ended up showing up twice. We just don't know. So this would be A, B, C. What about this one? This would be dx plus E, and this one would be fx squared plus gx plus I. H, and it doesn't matter. If you could pick any letters you wanted, it would work. So it appears as though we've made this way more complicated. We started with one variable, and now we have many variables. Okay, but what you end up doing is you take all these partial fractions and you turn them into the common denominator, and that's going to build a system of like 8 equations. And every equation is going to have some form of A and B and C and D and so on. And then you just stick those numbers in your matrix and do a reduced row echelon form, and it will tell you the values of A, B, C, D, and you plug them in, and a lot of them are going to end up being zeros. And that will tell you what number goes here, and what number goes here, and this one might disappear. Well, anyway, yeah. And this might disappear, and we just have that. And you end up essentially undoing that whole adding fraction common denominator. So, the idea behind partial fraction decomposition is we know how to take rational expressions, find a common denominator, add them together, and get the simplified version. But in calculus, that more complicated fraction makes calculus very, very, very difficult. So if we know that answer, it's not too hard, I mean, a little bit rough, but it's possible to take that simplified fraction and revert it back to the original decomposition fraction, and then you can treat each fraction separately with calculus, which is much easier. Now, having said that, what if we find common denominators, and then at the end we simplified? In theory, there are an infinite number of possibilities, but one is all we need. The most simple one is what this is going to calculate for us. Okay, so let me start with this. Okay, hold on. Don't do your book yet. Look up here. All right, so first off, I have to double check, are any of my quadratics factorable? This one is x plus 5 and x minus 1. Do I have any quadratics? No. All of my factors are linear. 2 of them are squared factors, but the most simple version they're still linear. So my partial fractions would be x squared, x minus 5, x minus 5 squared, x plus 5, and x minus 1. And they're all linear, so it's just going to be A, B, C, D, E, and F. And I'm done. Well, tomorrow we'll figure out how to calculate A, B, C, D, E, and F, but we're not going to mess with that today. That's as far as we're going to go for a minute. All right, what about this? Okay, let's do this, then we'll do a new one. So don't work on your set yet. There's some stuff I haven't taught you, or that we haven't really gone over. So whatever the numerator is, we don't care. All we're doing is setting up the partial fractions. So what are my partial fractions? So this factors into x minus 3 and x plus 3, both linear. So x minus 3 and x plus 3. And then that last one, does it factor? Are there two numbers that multiply to be 6 and add to be 2? No. So that is a quadratic factor. So this would be A, this would be B, and this would be CX plus D. Okay? Now, what if I squared this? So now I just have a duplicate quadratic factor, so x squared plus 2x plus 6 squared, and my numerator is, it's still linear, so ex plus f. Okay? Well, what if I squared this? Then both of these could have a squared on them, so I would have x minus 3 squared and x plus 3 squared, but the numerators they still have to be constants because the denominators are just squares of linear factors. So this would be g, and this would be h. Rain, did you have a question? Does that happen? I don't think that's ever going to happen. Well, you can't have a 6 in the bottom because you can't make 6 a proper fraction, right? It would be 6x to the 0. So if you had a 6, it would actually be in here. It would be part of some other factor that had an x in it. Or you could just pull it out and ignore it and then put it back in later. But I don't think that I can't ever remember that happening. All right, so look on page 872. The first set is really easy. You have 6 fractions, and you need to match it with its appropriate partial fraction decomposition. So it's just a matching game. That's pretty easy. And this is, sorry, let me write this up. 872, it's 1 through 14 all. 7 through 14, you need to do your own partial fraction decomposition. Okay, now, the answers in the books might have the A's and B's in different places, because there are lots of ways that you could combine or permute those fractions. But as long as you have the same denominators, and you make sure that quadratic factors have linear numerators, and everything else has a constant, then it's the same answer. Okay? It doesn't matter what order you write these fractions in, even though the A's and B's are going to be all mixed up. In the end, when we solve them, it'll work itself out. Yeah, we don't care about the numerators today. The numerators will come into play tomorrow. So if you did, let's do an odd one, or an even one. Let's do 10. Look at number 10. So number 10, all we care about is the denominator. x to the fourth minus 9x squared. Does that factor? It's x squared times x squared minus 9. Does it factor further? X squared times x minus 3 and x plus 3. Do I have any quadratic factors? No, my three factors are x, x minus 3, and x plus 3, but x has a multiplicity of 2. Even though it's x squared, it's not a quadratic in this case. It's the root 0 twice, essentially. So the graph of just this is going to look something like, so we have negative 3 as a root, 0 is a double root, and then, so I really only have three factors, but one of them has a multiplicity of 2. So my partial fraction decomposition would be a over x plus b over x squared plus c over x minus 3 plus d over x plus 3. And luckily, we don't get into the x to the thirds, because then you end up having quadratics in the numerator, and it ends up being the same, but you do a lot more algebra. Yes, Abe? Okay, number 11. So 11, does 11 factor? No. So what are we going to do? So what does the answer say? Let me look at it.
2x minus 6 plus 3x plus 33 over x squared.
Where is it?
X minus plus 5.
Oh, why did she do this? Okay, so I didn't realize she had done this. So is number 11 proper? It's not proper. So I better show this to you. So I'm not going to make you do any of this, but just in case it shows up on the final. So number 11 is not proper. So what we need to do is divide it, and we have to use long division. Synthetic division won't work. So we divide it, and we're going to get something with a remainder, and that remainder is guaranteed to be proper, right? The remainder is always less than the original denominator, so we would divide it. So x squared, x, and 5. So this is 2x to the third. That goes in 2x times. And then this would be 2x squared. And that would be 10x. And then this box and this box need to add up to be negative 4. So this would be minus 6x squared. Nope. Oh. Yeah, x squared. So this would be minus 6. Negative 6 times x is negative 6x minus 30. So then this box and that box have to add up to be 7. 2 minus 6 is negative 4. So it would be 11x. So this would be plus 11. So this... Oh, I mean my remainder. Thank you. So 11x. And then this one and this one have to add to be 3. So that would be 33. So my remainder is plus 11x plus 33 over x squared plus x plus 5. And that's what you do the partial fraction decomposition on. But all we have is a quadratic factor, right? The denominator is just a quadratic factor. So if I wrote the partial fraction decomposition, the only option is x squared plus x plus 5. So it would be ax plus b. But guess what? We already know what a and b are, so in that case, there was no point in doing it. So the same thing's going to happen for number 12. 13 is not. 13 is proper. There are more x's in the bottom than there are on the top. So 14, is 14 proper? Yeah, we have x to the fourth and bottom, on the bottom. So I guess for 12, number 12, just do long division and you're done. Okay, I thought she was going to make you do long division and then do partial fractions, but in this case you didn't have to, and the next one you won't have to either. Okay? And then bring your algebra skills tomorrow because we're going to be multiplying polynomials like crazy. And then we'll plug them into your calculator in these huge matrices. And then do the RREF and it will simplify down. And it will tell us what A, B, C, and so on are. All right? Good luck.